just took a while, but good things sometimes take time. I'm super happy to welcome Rana Hanocka. She's an assistant professor at the University of Chicago and also appointed at the Toyota Technological. No? Can you hear me? Better now? Okay, so I'm super excited to have Rana Hanocka here. She's an assistant professor at the University of Chicago and holds an appointment at the Toyota Technological Institute at Chicago as well. And she founded the 3L Research Collective, comprised of enthusiastic researchers passionate about 3D, machine learning, and visual computing. She did her PhD at Tel Aviv with Daniel Cohen-Orr and Raja Gires, and research interest really includes harnessing the power of retrained 2D foundation models for geometric processing tasks, crucially without any 3D data. So let's give her a warm welcome.
Hi, everyone. Thanks for showing up early in the morning. Hopefully this will be an exciting talk. Today I'm going to talk to you about some of the work coming out of my group at the University of Chicago. A lot of computer graphics and computer vision researchers are really excited about the promise of neural representations like Gaussian splatting or NeRFs. And they've shown like a lot of promise for different applications like novel view synthesis and scene reconstruction. But meshes are the industry standard. When a 3D animator goes to create something for a game or a movie or an animation, they use a mesh, and meshes are built, the entire graphics pipeline is built around meshes. I believe that we should create 3D content by editing meshes as opposed to going through NeRFs, and that's for a few reasons. The first is that meshes accurately represent sharp features of the shape, the topology, the underlying structure. The second is that we if we want to use this representation in a graphics pipeline, we need to convert to a mesh, and going from NeRFs to meshes isn't easy. So even though the neural render might look good visually, when we go to extract the mesh under the hood, it may look sort of messy and have tons of artifacts. Finally, if we kind of like shift this paradigm into providing like an input mesh to start with, then this gives kind of more user control, which is really what artists want. They have a specific vision that they want to execute. So this is a prior work from our group in CVPR a few years ago. A second challenge is that where are we getting all of this data from? Deep learning systems are extremely data hungry. And this is regardless of whether this data is sort of supervised or unsupervised. And I would like to argue that even if we're training on large amounts of unsupervised data, like just unannotated meshes, that still requires curation. Even in the case of images, we have to clean, frequent update, consolidate, potentially deal with copyright issues. So in 3D, it's even more challenging to acquire large 3D data sets. There's many, many reasons for that. The first reason is that it's sort of a sad state of computer graphics that it's really challenging and mentally taxing even for seasoned experts to create 3D objects. And even after they've sort of meticulously gone through this process and created 3D shapes, they're not necessarily compatible for our geometric computation, which means that we'll end up kind of discarding a lot of this data because our geometry processing algorithms won't effectively work on this type of data. So these are just a couple challenges that I mentioned, why it's hard to sort of train on these large-scale 3D data sets. And I believe that if we move beyond having to train on large-scale 3D data sets, we can catalyze progress in different fields in geometry processing and solve a whole host of problems that we don't currently have the data for and we never may be able to get the data for. And sort of the key nugget that I'm going to push in this talk is that we can actually leverage these very powerful 2D foundation models that have trained on tons of images out there in the wild and use that as a signal to do something with our geometry. And the key way that we can do this is essentially through inverse graphics. So we can connect the geometry to a differentiable rendering in the image and kind of use that to do something meaningful on the geometry itself. This is really nice because it helps us take advantage of these really large 2D data sets that other people have kind of worked hard to consolidate for us. And a kind of nice feature is that images are sort of natural way of how we perceive the shape. This is how we look at a shape. We look at a 2D projection of it. So in my group at the University of Chicago, we've kind of pushed this line of works of editing meshes. And a key feature of these works is that we don't use any 3D data sets. And I'm going to talk to you today, unfortunately, not about all of these works, but I encourage you to check some of them out if they pique your interest. I'm going to start with some works that deal with localization. So in this work, which we presented in CVPR a couple years back, we were really interested in trying to sort of figure out what do these 2D models know when it comes to 3D. And that really started from some of the results from our prior work, text to mesh, so given this input shape on the left, the result of our work is on the right here. When you give it a text prompt, Steve Jobs, it kind of stylizes the shape in this way. And this wasn't the only result that looked like this, but it made us ask the question, can we extract this underlying analysis that's inherent in this synthesis process? So what do I mean by that? I mean, you see that the facial hair on Steve Jobs is in the place where you expect facial hair to be. The shirt folds are where you expect them to be, and the creases of the pants are also where you expect them to be. But we don't have any explicit segmentation. And the question is, can we tease this segmentation out of this process? Can we get explicit access to what is the location of, for example, the shirt on this shape? And so our 3D highlighter answered this question. Yes, we can localize regions on a shape using text as input. So if we start with this 3D shape and we input to our system necklace, we get the vertices on the shape that correspond to where a necklace might go on a horse. And it's giving us the explicit sort of set of vertices that correspond to that region. The one thing that I think is kind of interesting about this work is that we're doing some type of higher level understanding and analysis on these shapes, which kind of goes beyond a sort of classic segmentation type approach. So you can't just sort of look at the local geometry on the human and say, where is a necklace? Because there is no necklace, right? But a 3D modeler may want to put a necklace on this human, and that seems like a reasonable location to do that. And a more interesting example, in my opinion, is like the poncho on a horse, because horses clearly don't wear ponchos. This is not part of any sort of data set. But the system needs to reason about what is a horse, what is a poncho, and where could it ostensibly go on a horse. And so the sort of gist of how this works is that we reformulate this problem to explicitly perform analysis and use that for synthesis. So previously in our work, text to mesh, the key idea there was that we had some mesh and we predicted over that mesh some style attributes, so color and displacement. And in this work in 3D highlighter, what we said is, let's predict localization attributes, so literally probability values, and use those probabilities to blend colors onto the mesh. And then we're going to kind of supervise on this probability guided coloring. So that's kind of the key idea. And the way this works, like in a little more details, is we start with some input mesh. We pass all of the vertices of the mesh through like an MLP. And then we predict for every single vertex, what is the probability that that belongs inside the region of hat on this cow. And then we blend the probabilities onto the mesh with strength proportional to the probability itself. So if it's probability 1, we put yellow. If it's probability 0, we put gray. And if it's probability 0.5, we put somewhere in between. The question is, how do we supervise this thing? We don't have sort of any 3D data set that corresponds to this task. And we definitely don't have like pairs of text and annotations. And so the key idea in this work and in the works I'm going to talk to you about is that we're going to supervise by essentially differentiably rendering this thing, seeing what the images look like in the visual space, and using that to update the geometry. So in this case, we used a clip, but spoiler alert from the future, we also tried like diffusion SDS, and that also works quite well. So the idea is we render this thing for multiple views, we pass the text prompt into some visual loss, and then we use that to update the neural highlighter. So we used this highlighter, like just to sort of emphasize the point that this is not just yellow blobs. These are actually localizations. We put textures inside of these regions, and you can see that we can get kind of explicit localized editing. We also have this nice ability to do this controllable compositionality. So we could take the body of Steve Jobs, the body of Iron Man, the head of Steve Jobs, and the legs of a Yeti, and kind of compose them together in an explicit way. We can also do some type of geometric edit, so we can stretch things or extrude them along the normal direction. So all of these results were pretty amazing to us and made us sort of think, how can we push this even further? And so what we decided to look at is, can we do these things together in tandem? Can we predict a localization and a texture map together? And the hypothesis is that if we do these things together, we're going to get a better one of each. And that's kind of what you can see here, that we're getting really fine-grained, like chain links on this necklace, and some high-quality textures that correspond to it. So you can see here, again, how kind of accurate and fine-grained these results are. I would really like to push this idea that, this task is really hard. Like, there's no place to hide on this gray mesh. If we're kind of inaccurate in any way, you will see like lots of artifacts. So the fact that we can kind of predict, for example, these different local texture edits on this shape, and then we could go and we can composite them together, one on top of the other. And the fact that, we don't see any fringing or boundary artifacts is because of how precise these local textures are. So the gist of how this works, this has like a few moving parts, but just kind of like the high level idea is that we take some input mesh and we do two high level things to it. There's like more if you check out the paper, but if you understand this, you kind of understand the gist of how this is working. So we have one branch that says, let's predict this localization in a very similar way to highlighter and like penalize what that looks like from a visual loss perspective. And then we have a second loss that looks at predicts a texture and masks that texture explicitly with the predicted localization. So we're not just predicting the localization, we're actually using it to mask out the predicted texture. And again, we differentiably render this thing from multiple views and use some type of visual loss. So one really fun nugget of this work that my PhD student Dale, who presented this work and the prior work, showed is that we can do something a little more interesting than just SDS. So most people use SDS, which is the first stage of a cascaded diffusion model, the base stage. So that's the top row here. And with this work, we said, why just use the first stage of a cascaded diffusion model? Why not use kind of all of the stages? And so that's the result of using CSD, cascaded score distillation, at the bottom row here. So just just to show you a little bit more about this CSD and to talk you through it a little more. So a cascaded diffusion model takes text as input, predicts a low resolution image, and then has a second stage which takes that low resolution image and upsamples it. And so if you just use the first stage of this model, which is SDS, you get something that sort of makes sense, right? You have a sort of low res, but structurally correct result. So the fancy gold watch is in the right place, but has kind of low details. If you just use the second stage, then we don't get the right location, but we kind of get fine-grained details, which also makes sense because the upsampler is just taking the sort of given low-res result and upsampling it. And then if we combine them together, we get the right location and the correct amount of details. So that's a really nice feature of this. And we can kind of blend and control the strength of these different properties of the cascaded diffusion model. So here's a bunch of fun assorted results to stare at. I want to highlight, I guess, just a few of them. So first is that you can see the really high details on this Barcelona jersey and the wrinkles on the cape of this dog. And you can see that the localizations, the segmentations that we predict are really sharp and precise. You can see the exact sort of Batman emblem and the like straps for the flip-flops. So to sum up this kind of section of the talk, we extracted this underlying analysis that's clearly inherent in the synthesis process. A nice feature of this work is that we get explicit and fine-grained control over these like segmentation masks. And we can exploit these pre-trained 2D foundation models to do segmentation in 3D. Here's a teaser of a like in submission, hopefully on archive soon work by Dale. And so what he said is that, well, you know, images are worth 1,000 words, right? We're in the pixel community. Why use text prompts? Let's use images. They describe things that cannot be described by images, right? You cannot describe the texture of this shirt with text. You need an image. So yeah, that's hopefully something to check out soon. Okay, so that concludes the first part of the talk. In the second part of the talk, I'm going to talk about deformations. And specifically, we had this work that was presented in 3DV a few months back. And what we saw with this work is that we can do extremely expressive deformations of meshes using text prompts. And I want to just say at this point, I've been up until this point, like extremely impressed with what we could do with these pre-trained models, but I feel like deformations is kind of like the next level of what we can do with them. And so I really want to push that even further with this work. So here's some results. So if you start with this input shape and you specify Yoda, here's what you get. And here's another result. So the thing about this work is that it's extremely general and can do highly expressive mesh manipulations. And I think a natural question that you might ask is, well, why not just use these like sort of text to 3D from scratch? If I didn't convince you in the first couple of slides, the point is that the renders, the the neural renders might look good visually, but when we actually go to extract these meshes in post-process, we get a ton of artifacts, missing parts, floaters, undesirable triangulation. Sort of the list can go on and on. But because we start with an initial mesh, the triangulation of our result is nice, which makes it sort of a practical use case. So Meshup is a general framework, and it has a bunch of different sort of modes you can toggle. But sort of the most bare bones mode of Meshup is that you start with an input shape and you deform it. And one kind of key insight of that work is that we should represent deformations through Jacobians instead of directly displacing vertices. So this was an insight that was taken from NJF, neural Jacobian fields, and also our prior work, text deformer. And essentially what we do is we predict these Jacobians per triangle, and then we use those to deform the shape. This is, again, instead of displacing vertices. We render the resulting shape from deformed shape from multiple views and pass each of these views through a denoising network. So hopefully if you're listening at this point, the question is, how do we supervise this thing? Well, visual loss. So we take score distillation, sampling loss, and we use that to backpropagate to update the Jacobians themselves directly. So I don't know if I highlighted it before, but like I want to highlight it again now. The fact that we have no supervision for this task, like we don't know how to take a cow and turn it into a turtle, like what is the deformation space there? And the fact that we can just render this thing from multiple views and get a signal that actually pushes this thing in the right direction is still mind-blowing to me. So this is just like a single target version of this. Meshup can also do other things. So one thing is that it can mix different concepts together. So you can make this wolf into a 60% fantasy couch and 40% robot dog. The way this sort of works at a high level is we essentially, again, predict Jacobians per triangle. And we have we have like multiple diffusion branches running in parallel. So we render the estimated deformation at a particular point from multiple views. We pass, let's say in this case, 2 desired text prompts into these denoising diffusion branches. And then we inject the intermediate activations into a primary diffusion process, which is conditioned on the null text prompt. And then we have, instead of like just a score distillation sampling, we have a blended score distillation sampling objective that we can use to update the Jacobians. So that's kind of the overall high level idea of how this works when we do mix multiple targets together. Another fun thing about this pipeline is that we can get localized control over where the deformation manifests. Another, again, fun thing about this work, like I said, very general kind of deformation pipeline. You can take some coarse or any 3D object as input and use a target image. And so a little bit different than the previous work, we used a textual inversion to sort of describe the image at a high level. So we're not going to get like perfectly accurate image reconstructions, but sort of like in the inspiration of these images deform the input shape. So all of these questions sort of led to this work that we're presenting in this coming CVPR. So please come talk to us at our poster session on Sunday afternoon from 2 to 4 if you are interested. We sort of wanted to say, okay, these deformations that we got in Meshup were highly expressive, almost to the point where we're sort of losing the identity of the input shape, and we kind of want to preserve that, right? And so that's what we decided to do in this work. We said, okay, here is some input 3D shape, and here's the text prompt cute animal themed chair. Here's the deformation result. So we can see that on the one hand, we're preserving the input shape, but on the other, it's still kind of able to express this text specified deformation. The key insight for how we gain more control over the deformation process is that we essentially reformulate how we decide to deform the shape. Instead of through these like free-form Jacobians, we sort of questioned that choice here and said, let's think about a different way to do deformations that's more restrictive, but still expressive enough. But you can see here, even though it's restrictive, we can still do things like add sort of high frequency textures, mid-low frequency changes to the shape, but still kind of overall preserving the content a little better. So here's one kind of key nugget of this work, is that we should use surface normals to describe the deformation. So here's how this works. We have some input shape that has a target normal per vertex, and then our system predicts a target normal. And we essentially set up this like recovery problem using a Procrustes solve to fit a best rotation from the source normal to the target normal. And this is like a differentiable operation. So this Procrustes solve has a like lambda parameter that controls the strength of this deformation. So higher lambda means we're going to fit this rotation per vertex more accurately to each target normal. This is clearly more restrictive than Jacobians. I were only able to describe like a rotation from a source to a target normal, but it's still expressive enough, as you could see in the previous slides. So this piece is sort of one smaller component in a larger layer that was presented in this work, which is called DARAP, a differentiable as rigid as possible layer. So the local step that I just described is essentially solving for this optimal rotation based on a target normal using that Procrustes solve. So now we have local rotations per vertex. And then we have a global solve that takes all of these local rotations for vertex, which would essentially, if you visualize that, give you like a triangle soup, and connects them all up together to give you a global like overall deformation. So a nice feature about this layer is that classical ARAP, classical as rigid as possible, will do local global optimization iteration until convergence. But because we present this in a layer, it turns out that we can just do one local step, one global step, and then we're done. So that's nice. So here's the high level gist of our approach. We take some input shape, some target text prompt, and then we optimize a normal per vertex. We pass that normal into this Procrustes solve, differential Procrustes solve. We get a local rotation. We pass the local rotation to a global solve, and then we get the final result. Of course, how do we supervise this thing? Well, we don't have a 3D data set or pairs of text and 3D style. So hopefully at this point, you're shouting out the answer. Use a visual loss. Differentially render this thing and look at it, what it looks like from multiple views. Again, I cannot kind of hammer home how impressive I think this is, that we literally do not have any ground truth sort of where should each of these vertices go. It just falls out from rendering this thing and asking a pre-trained foundation model, what should we do? So here's how it works in a little more detail. So we start with an input mesh. We predict for every single vertex on that mesh a target normal. And then we do this Procrustes solve to get a local rotation per vertex. And then we chunk everything up to get this global deformation, differentiably render this from multiple views, pass the desired text prompt into the semantic loss. In this work, we used CSD from Paintbrush and backprops that to directly update the target normals. But again, semantic loss is general. We also showed that we could use SDS and other types of visual losses here. So a nice feature of this work is that we get a lot of like fun control here. So we set, if you remember, I talked about a lambda parameter that kind of defines how well should we try to fit these rotations to the target normals. If we have some fixed sort of lambda 8 in the middle here during the optimization, in post-process, without sort of retraining or anything, we can sort of tweak that lambda and get better adherence to the target normals that were predicted. So that's kind of a nice feature of this. Another thing that was pretty surprising to me is that we could literally just do localized deformations by like, okay, you can manually select this region, you could have highlighter select this region, and then just deform the vertices inside of the selected region and set all vertices outside that region to identity. And it just works, like there's no boundary artifacts. And I think my sort of hypothesis is that this is like the smoothness of our DARAP layer in our kind of formulation. So here's just a few more results to stare at. We can stylize different shapes towards the same text specified style, in this case, different vases to Lego bricks. Or we could take the same shape and deform it towards different text specified styles like a retro game joystick, braided pillar candle, or upright fountain pen. So in sum, we can achieve these really highly expressive text specified deformations with Jacobians, but that's kind of a double-edged sword, right? Like we can do really expressive things, but maybe that is almost too much sometimes. And so we were able to really kind of rein that in with the surface normal based deformations. and preserve the input a little better. So just to tease you on something that we're currently working on, all of these kind of deformation-based works really said, let's keep the underlying mesh triangulation and just move the vertices around. But one thing that seemed really interesting is that can we insert new vertices? Can we add new mesh elements that didn't previously exist? And so hopefully you'll be seeing this work from us pretty soon that says that we can actually do this as well. Okay, so I presented to you a couple different works in localization and deformation buckets, but I'd love if I had more time to talk to you about more of some of our work, so please do check them out that do all of these fun tasks on meshes without any 3D data. Okay, so I believe that there is a ton more to do here. Like we're really just getting started. What other tasks can we solve in geometry processing? Like, can we detect symmetries? Can we predict vector fields on surfaces? Like, what else can we solve with this type of paradigm? I'm really interested in that. So if you have ideas, please come talk to me. What other properties can we extract from these models? Like, what else do they know? We saw that we can extract segmentations, but do they know more things about the geometry? A lot of, like, basically all of these works sort of generate a single example in an optimization type paradigm. But I think one promising direction, which sort of contradicts this 3D data set thing, is like, can we just generate a bunch of data using these approaches and then train a feed-forward neural network to sort of reproduce these optimization results? So with that, I just want to put up a plug for my for my group at Friedel at the University of Chicago. We're located in the modern city of Chicago on a sort of historic campus in a modern CS building. So if you're coming through Chicago, please do reach out to me or one of my students and come visit us and say hi. Thanks.